Something just tore loose from the sun, and we almost missed it. An M3.3 flare erupted yesterday from the far side of our star, hidden behind 900,000 miles of plasma. The official classification reads moderate. But here's what they're not telling you. This wasn't a flare. It was a warning shot. In exactly 5 days, the sunspot responsible for this blast will rotate into direct alignment with Earth, and it's doing so during a planetary convergence that hasn't occurred since 1936. The last time this geometry appeared, telegraph systems across 2 continents went dark. So stay with me, because by the end of this investigation, you'll understand why in just 5 days we might rewrite everything we thought we knew about space weather. The countdown has already begun. You'll want to subscribe and follow along, because we're venturing into space weather's most controversial territory. The data exists, the historical patterns persist, but the mechanisms remain unproven and carefully avoided in official bulletins. The next 5 days will provide answers one way or another. Something exploded on the sun yesterday. You probably didn't hear about it. The official classification came through as an M3.3 flare, which in the language of solar physics translates to moderate, the kind of event that happens dozens of times during an active solar cycle, the kind of thing that gets a line in the space weather bulletin and then gets forgotten by lunch. Except this one won't let itself be forgotten. The flare erupted from the far side of the sun, hidden behind the solar limb where our instruments can barely see. The X-ray detectors picked up the signature, ran their calculations, stamped it with that M3.3 label, and moved on. But here's the thing about labels. They're only as good as the context that creates them. When you're measuring an explosion through 900,000 miles of solar plasma, when the blast is partially obscured by the very star it's erupting from, your measurement isn't capturing the event. It's capturing an echo. The sun is a sphere, obviously, and we only ever see one hemisphere at a time. When something erupts on the side, facing away from us, the X-rays have to punch through layers of the solar corona, through the chromosphere, sometimes even grazing the edge of the photosphere itself. Every layer absorbs energy. Every layer attenuates the signal. By the time that radiation reaches our satellites, it's been filtered, diminished, categorized, according to what survived the journey, rather than what actually happened. This is not a conspiracy. This is geometry. Far-side flares are systematically underestimated. Everyone in the space weather community knows this. The classification system was designed around Earth-facing events, where the blast comes straight at our instruments with nothing in the way. When you rotate that same explosion 90 degrees, hiding it behind the solar limb, the numbers collapse. An X-class monster can read as a mid-level M. A civilization-threatening eruption can get filed under moderate activity. So, what actually happened yesterday? The flare lasted over 4 hours. Let that sink in for a moment. Most solar flares are measured in minutes. A typical M-class event might sustain peak energy release for 10, maybe 20 minutes, before the magnetic field reconfigures and the explosion chokes itself out. 4 hours means something else entirely. 4 hours means the magnetic structure feeding that eruption was massive, complex, and obscenely well-stocked with energy. The flare wasn't a sudden rupture. It was a sustained burn, like a dam with too many cracks to plug at once. Long-duration flares have a personality all their own. They don't just fling radiation into space and call it a day. They rearrange the solar corona. They excavate magnetic field lines that have been twisted and compressed over days or weeks. They dig deep into the active region's stored energy and dump it all at once into the heliosphere. And here's the kicker. Long-duration flares almost always come packaged with coronal mass ejections, not the little puff of smoke CMEs that dissipate before they reach Mercury. The big ones. The structure-altering, magnetosphere-compressing, civilization-noticing ones. This flare had a companion. The coronagraph images showed a massive CME tearing away from the sun's western limb, a towering arc of plasma and magnetic field racing outward at somewhere north of 1,000 kilometers per second. The geometry was awkward. The blast wasn't aimed at Earth. It was aimed slightly away, maybe 20 or 30 degrees off our celestial longitude. In the official assessment, that makes it a non-event, a miss. Move along. But space is not empty. Space is structured. The solar wind doesn't flow in straight lines. Magnetic fields don't respect Euclidean assumptions. A CME that grazes past Earth's orbital path can still deliver a glancing blow to our magnetosphere, especially if the background solar wind has already primed the environment. And our instruments did detect it. Faintly, obliquely, like hearing thunder from a storm that's technically in the next county over, but still close enough to rattle the windows. There's a gap between what gets said publicly and what gets discussed in the back channels. Space weather forecasters have two vocabularies. One is for the press releases, the official forecasts, the 5-day outlooks posted on government websites. That vocabulary is cautious, hedged, wrapped in probabilities and caveats. The other vocabulary is for the group chats, the late-night emails, the conversations between scientists who have seen enough solar cycles to know when something doesn't fit the pattern. Yesterday's flare is living in that second category. The official line is that this was a far-side moderate event with minimal Earth impact. The unofficial line is that we just watched a pressure release valve blow on a region we haven't even fully observed yet. Solar flares don't happen in isolation. They're symptoms of magnetic instability. When you see a long-duration eruption like this one, you're not looking at the problem. You're looking at the evidence that a much larger problem is still cooking beneath the surface. Think of it this way. Imagine you're standing outside a building and you hear a small explosion from somewhere deep inside, muffled by walls and distance. You can't see the source. You can only measure the vibrations that made it out to where you're standing. Do you classify the event based on what you detected, or based on what must have caused it? The flare yesterday was the muffled explosion. The Sunspot group rotating toward us is the building, and in about 5 days, we're going to see what's inside. History has a way of foreshadowing itself. There are patterns in the solar record, cases where a far-side eruption from an emerging active region turned out to be the warm-up act. 1989, 2003, 2012. In each case, the region announced itself with a sideways blast before rotating into view and unleashing something far worse. The Halloween storms of 2003 started exactly this way. A limb eruption, an underestimated classification, and then, 3 days later, the region turned earthward and went supernova. This is not to say history will repeat. The sun is not obligated to perform on cue. But it is to say that we have been here before, and the script is uncomfortably familiar. The danger is not what already happened. The danger is what happens when this active region completes its rotation and faces Earth directly. When that happens, the geometry problem disappears. The attenuation vanishes. If this sunspot fires again, we will see it clearly. We will measure it accurately, and there will be no classification errors to hide behind. So if this is what leaked out sideways, if this is what we detected through 900,000 miles of obstructing plasma, if this is the pressure relief valve opening, while the region was still pointed away from us, then the question becomes unavoidable. What happens when the nozzle points straight at us? The sun rotates. This is not news. It completes one full rotation, roughly every 27 days at the equator, slower at the poles due to differential rotation. Any feature on the solar surface takes about 2 weeks to cross from the eastern limb to the western limb as seen from Earth. Simple orbital mechanics. Predictable. Boring even. Except when the timing aligns with something else. Right now, that sunspot group is somewhere around 60 to 70 degrees past the eastern limb. It's rotating toward us at roughly 13 to 14 degrees per day. Do the math, and you arrive at a window. 5 days, give or take half a day, depending on how you calculate the exact longitude. That puts the region squarely Earth-facing, somewhere between January 18th and January 20th, 2025. Those dates should sound familiar if you've been paying attention to the sky, because January 18th through 20th isn't just when the sunspot arrives, it's when everything else arrives too. Let's start with the moon. On January 20th, we have a new moon. Not an approximate new moon, not a near new moon. An astronomically precise new moon, with the lunar phase reaching exactly 0 degrees separation from the sun as seen from Earth. In the language of celestial mechanics, this is called a syzygy, which is a magnificently weird word for 3 bodies in a straight line. New moons happen every month. This is also not news, but not all new moons are created equal. The moon's orbit is elliptical, and its distance from Earth varies by about 40,000 kilometers between perigee and apogee. During a new moon at or near perigee, the tidal forces are stronger. Not just ocean tides, atmospheric tides, ionospheric tides. The moon doesn't just pull on water, it pulls on every layer of Earth's electromagnetic environment. When the moon is directly between Earth and the sun, it creates a gravitational gradient that compresses the magnetosphere slightly on the day side and stretches it on the night side. The effect is subtle under normal conditions, but when the solar wind is already active, when the magnetosphere is already under stress, that lunar compression can be the difference between a glancing blow and a direct penetration. It changes the geometry of how Earth interacts with incoming plasma. But we're not done with January 20th. On the same day, Mercury reaches what's called a cazimi, an exact conjunction with the Sun as seen from Earth. Mercury will be passing directly between us and the Sun, though not quite aligned enough to produce a transit. The orbital geometry places Mercury at inferior conjunction, moving at nearly its maximum heliocentric velocity because it's near perihelion. Now, mainstream solar physics will tell you that Mercury's position is irrelevant. Mercury is tiny. Its gravitational influence on the Sun is negligible. The tidal force it exerts is orders of magnitude smaller than Jupiter's, and even Jupiter's tidal effect on the Sun is considered essentially zero in terms of triggering eruptions. This is probably correct. But there's a second conversation happening in the corners of plasma physics, one that doesn't make it into the standard textbooks. This conversation is about electric currents, not gravity. The Sun exists inside a vast circuit of charged particles and magnetic fields that extends throughout the heliosphere. Mercury, despite its size, moves through this circuit at high speed and with a magnetosphere of its own. Some researchers working outside the mainstream consensus suggest that Mercury's position might modulate the current flow in the solar wind, creating small but measurable perturbations in the local plasma environment. Is this proven? No. Is it widely accepted? Absolutely not. But it's a hypothesis that refuses to die, largely because there are correlation patterns in the data that nobody has adequately explained. And then there's Jupiter. On January 18th, Jupiter reaches opposition, meaning it sits directly opposite the Sun as seen from Earth. Earth, Sun, and Jupiter form a straight line across the solar system. Jupiter is the giant of the planetary family, holding more mass than all the other planets combined. Its gravity dominates the outer solar system. Its magnetosphere is so large that if you could see it from Earth, it would appear several times the size of the full moon. Does Jupiter's gravity trigger solar flares? Almost certainly not. The tidal force calculation is straightforward, and the numbers don't support it. The Sun is too massive, too energetically independent, too governed by its own internal magnetic dynamo to care about where Jupiter happens to be. But again, there's a parallel conversation. Some researchers point to long-term periodicities in solar activity that seem to correlate with Jupiter's orbital period. Others note that the solar wind carries energy outward through the heliosphere and interacts with planetary magnetospheres in ways we're only beginning to map. Could Jupiter's position influence the large-scale structure of the heliosphere in ways that feed back into solar behavior? Could the alignment of multiple planetary magnetospheres create resonances or current modulations that we haven't yet detected? These are speculative questions. Emphasis on speculative, but they're being asked by people with PhDs and decades of experience, which means they're at least worth stating clearly. So here's what we have. Between January 18th and January 20th, the Sunspot group reaches Earth-facing geometry. Mercury hits inferior conjunction. The Moon reaches new phase. Jupiter sits at opposition. These are not secret alignments. They're listed in any ephemeris. You can look them up on a dozen different astronomy websites. What's unusual is the convergence. Having all of these occur within a 48-hour window is not common. It's not unprecedented, but it's not common. The last time a similar clustering occurred during an active solar maximum was in 1936, and that event has become a minor legend in space weather circles for reasons we'll get to later. There's a term used informally among some forecasters for moments like this. They call it a convergence window. It doesn't appear in official bulletins because there's no accepted physical mechanism to justify it. You won't find it in peer-reviewed journals under that name. But it shows up in private discussions, in retrospective analyses of major geomagnetic storms, in the pattern matching that experienced forecasters do when the models aren't quite capturing the situation. The convergence window is not a prediction. It's an observation that certain configurations seem to correlate with elevated solar activity more often than random chance would suggest. Correlation is not causation, and everyone involved knows this. But when you're dealing with a chaotic, non-linear system like the Sun, correlation is sometimes the only warning you get. So, the timing is precise. Uncomfortably so. 5 days from now, a hyperactive sunspot group will rotate into direct alignment with Earth at the exact moment when Mercury, the Moon, and Jupiter form a geometric pattern that hasn't been seen during a solar maximum in nearly 90 years. If timing isn't random, the next question becomes uncomfortable. What exactly is being timed? Active regions don't usually announce themselves from behind the solar limb. Typically, you get hints. A brightening in the extreme ultraviolet. Maybe a small flare or two as the region rotates into view. But full-scale eruptions while still hidden? That's less common. That suggests the region is already mature, already magnetically twisted, already loaded with energy before we even get a clear look at it. This is exactly what we're seeing now. The region started firing while still behind the eastern limb. That M3.3 flare we talked about earlier wasn't the first activity from this area. There were smaller eruptions before it. C-class events that barely registered on the public radar, but showed up clearly in the full disk imagery. The region has been active for at least 2 to 3 days while completely out of direct view, which tells you something important about its magnetic structure. Solar flares are powered by magnetic reconnection, a process where twisted, stressed magnetic field lines suddenly snap and reconfigure into a lower energy state, releasing the difference as radiation and kinetic energy. For reconnection to happen, you need complexity. You need field lines that are wound up, sheared, compressed into configurations that are fundamentally unstable. The more complex the magnetic topology, the more energy can be stored, and the more violent the eventual release. Think of it like tensioning a spring. A simple spring stores a predictable amount of energy based on how far you compress it. But a spring that's been twisted, bent sideways, compressed unevenly, and then twisted again. That spring is storing energy in multiple dimensions, in configurations that want desperately to snap back to equilibrium. When it finally releases, the motion isn't clean. It's chaotic, multidirectional, and potentially far more energetic than the compression alone would suggest. That's what's happening in the magnetic field of this active region. The field lines have been tortured into a configuration that's begging for release. When forecasters classify sunspot groups, they use a system called the Macintosh classification, which describes the size, shape, and magnetic structure of the region. The system uses a 3-letter code that captures everything from the basic size of the sunspot group to the complexity of its internal structure. Simple regions get simple codes. Complex regions get codes that make forecasters reach for their coffee and start watching more closely. But there's a special category that gets extra attention. Delta-class regions. These are areas where opposite magnetic polarities are jammed together in the same penumbra, creating extreme shear and enormous potential for eruption. In a normal sunspot group, the north and south magnetic poles are separated, like the ends of a bar magnet laid flat on the solar surface. In a delta region, those poles are crushed together, intermingled, forced into unnatural proximity. Imagine trying to push the north poles of 2 magnets together. They resist. They want to fly apart. Now, imagine holding them in place with tremendous force while also twisting them. The energy you're putting into that system doesn't disappear. It gets stored in the magnetic field, waiting for the moment when your grip slips. Delta regions are responsible for the majority of X-class flares. They're the powder kegs of the solar surface. When a delta region decides to erupt, it doesn't ask permission, and it doesn't give much warning. We don't have full imagery of this region yet, but the eruption pattern suggests delta-class characteristics. Multiple eruptions over several days, long-duration events, strong CME production. These are the signatures of a magnetically tortured active region, one that's been building tension for days or weeks and is now beginning to unload. Here's where the public communication gets tricky. Space weather agencies are conservative by design. They don't issue alerts based on partially observed regions. They don't speculate about worst-case scenarios when the data is incomplete. This is reasonable. This is how science-based forecasting should work. You wait for clear observations. You run the models. You issue forecasts based on what you can measure rather than what you fear. The alternative would be a constant stream of false alarms, every ambiguous signal treated as an incoming catastrophe, every partial observation escalated to maximum threat. That's not forecasting. That's panic distribution. So the agencies err on the side of caution, which in this context means waiting for certainty before sounding the alarm. But it also means that warnings lag behind reality. By the time a dangerous active region gets flagged as high risk, it's often already Earth-facing. By the time the models incorporate the full magnetic complexity, the flare may have already erupted. The system is designed to avoid false alarms, which inadvertently makes it better at confirming disasters than preventing them. So right now, this region exists in a weird liminal state. Officially, it's not a major threat because it hasn't been fully characterized. Unofficially, everyone watching the sun is paying very close attention to what happens over the next 72 hours. There's a phrase used in space weather circles, usually in private conversations, rather than public bulletins: active, but not yet designated. It means we know something is happening. We know it's significant, but we don't yet have the observational basis to make formal predictions. The region is Schrödinger's threat, simultaneously dangerous and benign until we open the box and look directly at it. One of the things that makes this region unusual is the eruption cadence. We're not seeing one big flare followed by quiet. We're seeing a sequence. Multiple moderate eruptions spread over days, each one releasing energy, each one reconfiguring the magnetic field, each one potentially setting up the conditions for the next blast. This is sometimes called a flare family, and it's more dangerous than a single extreme event. Here's why. When a sunspot produces one massive X-class flare, it often releases so much energy that the magnetic field simplifies. the tension unwinds. The region goes quiet for days or even weeks while it rebuilds complexity. It's like a volcanic eruption that empties the magma chamber. Once the pressure is released, the system needs time to recharge. But when a region produces a series of M-class and X-class flares over several days, it means the magnetic structure is fragmenting rather than simplifying. Each eruption is opening new channels, creating new instabilities, priming the region for further releases. The magnetic field isn't unwinding, it's unraveling. And an unraveling system can maintain high activity levels far longer than one that undergoes a single catastrophic release. From Earth's perspective, this is worse. A single X10 flare is dramatic, but Earth's magnetosphere can handle a one-time punch if it has time to recover. What it struggles with is repeated impacts. Multiple CMEs arriving over a span of days, each one compressing the magnetosphere, each one injecting energy into the radiation belts, each one straining the power grids and satellite systems that are already operating at the edge of tolerance. Think of it as the difference between being hit by one large wave and being caught in a series of medium waves that never give you time to catch your breath. The single wave might knock you down, but you can recover. The series drowns you. This is the scenario that keeps grid operators awake at night. Not the single solar tsunami, but the relentless drumbeat of moderate storms that never lets the system reset. Transformers that survive the first impact, but overheat during the second. Satellites that shrug off the first radiation dose, but accumulate damage during the third and fourth. Communication systems that degrade incrementally until they cross a threshold and fail completely. And this region seems to be following that script. The far side eruptions suggest a pattern of staged releases rather than one catastrophic unwinding. If that pattern continues after the region rotates earthward, we could be looking at multiple Earth-directed CMEs over a 72 to 96-hour window. Not necessarily larger than historical events, but more sustained, more cumulative, more systemically destabilizing. The official space weather dashboards update every few hours, but they're always playing catch-up with a chaotic system. The models ingest the latest imagery, calculate the magnetic field strength, estimate the flare probability, and output a percentage. 30% chance of M-class flares, 10% chance of X-class. These numbers are useful, but they're also backward-looking. They tell you what the region was doing when the image was taken, not what it's about to do. It's like trying to predict the weather by looking at photographs from 3 hours ago. The information is real, it's just not current enough to tell you whether to grab an umbrella before you walk out the door. Solar eruptions are fundamentally unpredictable on short timescales. We can't say with certainty when the next flare will occur, or how strong it will be, or whether it will produce a CME. We can only say that the conditions are favorable, that the energy is available, that the magnetic structure is primed. The rest is chaos. But there are patterns within the chaos. Regions that fire repeatedly tend to keep firing. Delta-class regions produce more X-class flares than simpler structures. Long-duration events almost always come with CMEs. These patterns don't give you precision, but they give you preparation time. And right now, the pattern says this region is unloading in stages. The question is whether we've seen the biggest stage already, or whether the main act is still waiting for an Earth-facing audience. There's also the matter of what we're not seeing. Behind the solar limb, our instruments are effectively blind. We can detect the X-rays that make it around the curve of the sun. We can spot the CME eruptions in coronagraph imagery, but we cannot directly observe the photosphere where the magnetic field actually lives. We're reading the symptoms without seeing the disease. Modern helioseismology can sometimes peek behind the limb by analyzing sound waves traveling through the solar interior, but the resolution is coarse and the lag time is significant. By the time we process that data, the region has already rotated further into view. So we're always operating with incomplete information, always making educated guesses about what's happening in the regions we can't directly observe. This region could be far more complex than we realize. It could be larger. It could have multiple delta cores instead of just one. It could be magnetically connected to other active regions in ways that create synchronized eruptions. We won't know until we see it fully. And in approximately 5 days, we will. A storm doesn't need to be bigger. It just needs to hit repeatedly. The solar wind reached Earth yesterday, moving at nearly 600 kilometers per second. That's fast. Not record-breaking, but fast enough to get attention. Normally, high-speed solar wind comes packaged with high density, a thick stream of protons and electrons that hits Earth's magnetosphere like a fire hose. But this wind was different. The density was low, unusually low. Less than 3 particles per cubic centimeter, which in the context of space weather is almost vacuum. This matters more than you might think. Imagine you're standing in a field and someone throws a baseball at you. That's high density, moderate speed. Now imagine someone fires a rifle in your general direction. The bullet is smaller, carries less total mass, but the speed and the sharpness of the impact create a different kind of problem. Low density, high-speed solar wind is the bullet. It doesn't bulldoze the magnetosphere with brute force. It cuts through it with velocity and precision. The physics here is counterintuitive. Most people assume that a denser solar wind would be more dangerous, that more particles equals more impact. And under certain conditions, that's true. A slow, dense stream can compress the magnetosphere through sheer mass, creating prolonged pressure that strains Earth's magnetic defenses. But a fast, thin stream creates something else entirely. It creates instability. When the solar wind is thin but fast, it creates what's called a dynamic pressure pulse. The magnetosphere compresses on the day side, stretches on the night side, and the boundary between the two becomes unstable. Magnetic reconnection occurs more easily. Particles from the solar wind can slip through the cracks in Earth's magnetic shield and penetrate deeper into the radiation belts. The system becomes brittle. Think of Earth's magnetosphere as a bubble in a stream. When the stream flows thick and slow, it pushes the bubble steadily downstream, but keeps it intact. When the stream becomes thin and fast, it creates turbulence. The bubble starts to wobble. Parts of it get pinched off. The boundary between inside and outside becomes permeable in ways it shouldn't be. And that's exactly what happened. Earth's magnetosphere responded to the low-density wind with a Kp index spike that hit 6, which officially qualifies as a moderate geomagnetic storm. Auroras appeared at mid-latitudes. Satellite operators got alerts. The power grid saw minor fluctuations. Nothing catastrophic, but enough to remind everyone that the system is always one good hit away from serious trouble. The Kp index is a measure of geomagnetic disturbance ranging from 0 to 9. Most days sit comfortably between 0 and 3. Anything above 5 starts causing operational headaches for technology dependent on stable electromagnetic conditions. 6 means auroras are visible in places like Montana and Minnesota instead of just Alaska. It means satellite drag increases, GPS accuracy degrades, and power grid operators start monitoring transformer temperatures more closely. But here's the thing. This storm happened before the Convergence window, before the Sunspot group fully rotates Earthward, before the new moon and the planetary alignment and all the other geometric coincidences that are lining up for January 18th through 20th. We're seeing KP6 on the appetizer course. What happens when the main event arrives? The radiation belts around Earth are already overcharged. These are the Van Allen belts, toroidal regions filled with high-energy particles trapped by Earth's magnetic field. During geomagnetic storms, these belts get injected with fresh particles from the solar wind. The energy builds. The flux increases. Satellites passing through the belts experience higher radiation doses. Electronics degrade. Systems fail. The Van Allen belts were discovered in 1958 during the early space age, and they immediately became a concern for mission planners. These regions contain protons and electrons moving at significant fractions of the speed of light, held in place by Earth's magnetic field, like particles in a cosmic particle accelerator. The inner belt sits roughly 1,000 to 6,000 kilometers above Earth's surface. The outer belt extends from about 13,000 to 60,000 kilometers out. Satellites in low Earth orbit skim beneath the inner belt. Satellites in geosynchronous orbit sit above the outer belt. But anything in between, anything in medium Earth orbit like GPS satellites and some communication arrays, spends its entire operational life bathing in high-energy radiation. The spacecraft are hardened against this environment, shielded with aluminum and specialized materials designed to absorb or deflect particles. But the shielding has limits. When multiple storms hit in quick succession, the radiation belts don't have time to relax. The particles accumulate. The energy compounds. You end up with a population of relativistic electrons that can punch through shielding and fry satellite components. This is not theoretical. This is how we lost several satellites during the 2003 Halloween storms. The Halloween storms of October through November 2003 remain one of the benchmark events in modern space weather history. A series of X-class flares erupted from multiple active regions over a 2-week period. The CMEs arrived one after another, compressing Earth's magnetosphere repeatedly, never allowing it to recover. The radiation belts became so overcharged that multiple satellites experienced critical failures. Some lost attitude control. Others suffered permanent damage to solar panels or communications equipment. A few were declared total losses. Right now, the belts are loaded. Not critically, but elevated above normal background. If we take another hit in the next few days, and then another, and then another, we could be looking at a genuine radiation hazard for satellites in low and medium Earth orbit. The operational lifetime of satellites is already marginal in many cases. Spacecraft are designed with expected radiation doses built into their mission planning. They accumulate damage over time, a slow degradation of electronics and solar cells that eventually ends the mission. But that timeline assumes normal conditions. It assumes the radiation environment stays within predicted parameters. When geomagnetic storms push the radiation belts into abnormal configurations, years of accumulated tolerance can get burned through in days. Then there's the power grid. Modern electrical grids are designed to handle predictable loads and predictable failures. A transformer goes down, you reroute. A line gets knocked out, you switch to backup. But geomagnetic storms don't follow the rulebook. They induce currents in long conductors, like high-voltage transmission lines, that flow in directions and magnitudes the system wasn't designed for. These are called geomagnetically induced currents, and they cause transformers to saturate, overheat, and sometimes fail catastrophically. Geomagnetically induced currents are essentially ground-level manifestations of space weather. When Earth's magnetic field fluctuates rapidly during a geomagnetic storm, it induces electric fields in the ground. These fields drive currents through any conducting path they can find, including the neutral grounding points of high-voltage transformers. The currents aren't huge in absolute terms, but they're direct current flowing through equipment designed for alternating current. Transformers don't handle this well. The transformer core begins to saturate asymmetrically. It overheats. The cooling oil inside starts to degrade. In extreme cases, the transformer can suffer permanent damage, melting internal components or causing structural failures that make the unit irreparable. And large high-voltage transformers aren't sitting in warehouses waiting for replacement. They're custom-built, take months to manufacture, and cost millions of dollars each. The 1989 Quebec blackout happened because of a geomagnetic storm. 6 million people lost power in 90 seconds. The grid collapsed like a house of cards because multiple transformers failed simultaneously, faster than operators could respond. The storm that caused it was rated as a G5, the most severe category, but it didn't take the strongest storm on record to knock out Quebec. It took a storm that hit at the right angle, with the right characteristics, at a moment when the grid was already stressed from other factors. Quebec's grid in March 1989 was running near capacity due to cold weather. The geomagnetic storm struck in the early morning hours when load was transitioning from overnight lows to morning peaks. The induced currents pushed several key transformers into saturation. Protective systems, sensing abnormal conditions, began opening circuit breakers. Within 90 seconds, a cascade failure propagated through the network. The entire province went dark. The power was restored within hours for most customers, but the event demonstrated a vulnerability that grid operators had underestimated. Modern grids are more robust in some ways, with better monitoring and more sophisticated protection schemes. But they're also more stressed, operating closer to capacity with less redundancy built in. We're not at G5 yet. We're at G2, maybe flirting with G3 if the next few days get interesting. But the grid is different now than it was in 1989. It's more interconnected, more dependent on real-time data, more vulnerable to cascade failures. The margin for error has shrunk. The trend in electrical grid design over the past few decades has been toward optimization and efficiency. Redundancy costs money. Excess capacity sits idle most of the time. Market forces push utilities to operate lean, to minimize infrastructure that isn't generating revenue. This works beautifully under normal conditions. It creates problems when conditions become abnormal. And there's one more thing. On January 11th, a magnitude 6.4 earthquake struck off the coast of Indonesia. Large, but not catastrophic. The kind of quake that happens somewhere on Earth every few weeks. Officially, this has nothing to do with the solar activity. Earthquakes are driven by plate tectonics, by stress accumulation along fault lines, by crustal dynamics that operate independently of space weather. Officially, but there's a persistent, controversial, and largely dismissed hypothesis that geomagnetic disturbances can influence seismic activity. The proposed mechanism involves changes in Earth's magnetic field, altering the electric currents in the crust, which in turn affects the piezoelectric properties of quartz-bearing rocks under stress. It's speculative. It's contested. Most seismologists think it's nonsense. But there are correlation studies that show a weak statistical relationship between geomagnetic storms and earthquake frequency in certain tectonic zones. The idea sounds absurd on its face. How could something happening in the magnetosphere influence tectonic plates grinding against each other deep in the crust? The energy scales don't match. The physical separation is enormous. The mechanisms seem completely unrelated. But Earth is an electrical system too. Currents flow through the crust constantly, driven by temperature gradients, chemical reactions, and the motion of ionized fluids through porous rock. Quartz is piezoelectric, meaning it generates electric charges when mechanically stressed. Some researchers have proposed that changes in the ambient electrical environment could alter the stress state of rocks that are already on the verge of failure, not causing earthquakes, but potentially influencing their timing. The Indonesia quake happened during the KP6 storm. That could be coincidence. It probably is coincidence. But when you're in the business of pattern recognition, coincidences start to look like data points. The broader issue is that Earth is not a passive target. It's a coupled system. The magnetosphere, the ionosphere, the atmosphere, the crust. They all interact in ways we're only beginning to understand. When you stress one part of the system, the effects ripple outward in nonlinear ways. A geomagnetic storm doesn't just affect satellites and power grids. It affects GPS signals, which affects aviation, which affects logistics, which affects everything that depends on precise timing and positioning. GPS satellites broadcast their signals through the ionosphere, a layer of charged particles in the upper atmosphere. During geomagnetic storms, the ionosphere becomes turbulent. Regions of enhanced or depleted electron density form and move unpredictably. Radio signals passing through these regions get delayed by varying amounts, introducing errors in the calculated position. For most civilian applications, these errors are annoying but manageable. For precision applications like autonomous vehicles, offshore drilling, or military operations, they can be mission critical. We think of space weather as something that happens up there, separate from daily life. But the infrastructure of modern civilization is threaded through with electromagnetic dependencies. We navigate by satellites. We communicate through ionospheric reflections. We synchronize financial transactions with atomic clocks that assume stable magnetic fields. When the space environment gets chaotic, the downstream effects are subtle at first, then suddenly not subtle at all. Earth's magnetic defenses are already under stress. The solar wind is fast and sharp. The radiation belts are overcharged. The grid is operating without margin, and we haven't even reached the convergence window yet. The sun doesn't have to break records. Earth just has to be unready. Let's be clear about what mainstream solar physics says. The sun is a magneto-hydrodynamic engine, driven by nuclear fusion in its core and shaped by convection, differential rotation, and a dynamo process that generates magnetic fields. Solar flares occur when these magnetic fields become twisted and stressed beyond their ability to maintain stability, leading to reconnection events that release energy. This process is governed by the internal dynamics of the sun itself, not by external influences. Planetary positions in this framework are irrelevant. The gravitational force exerted by even the largest planet, Jupiter, is minuscule compared to the self-gravity of the sun. The tidal bulge Jupiter creates on the solar surface is measured in millimeters. That's not enough to trigger anything. The sun doesn't know where the planets are. It doesn't care. This is the consensus view. It's supported by decades of research, by sophisticated models of solar magnetic fields, by statistical analyses that show no clear correlation between planetary positions and flare activity. When scientists say the planets don't trigger solar flares, they're not being dismissive. They're following the evidence. The mathematics are straightforward. Jupiter, despite being 300 times more massive than Earth, sits 5 times farther from the sun than we do. The gravitational force drops off with the square of distance, which means Jupiter's tidal effect on the sun is roughly 100 times weaker than the moon's effect on Earth. And the moon creates ocean tides, measured in meters on a relatively small rocky planet with liquid water. Jupiter creates tides measured in fractions of a millimeter on a massive ball of plasma, held together by gravity, so intense, it's fusing hydrogen into helium at the core. The numbers don't work. They're not even close. If you're going to claim that Jupiter triggers solar flares through gravity, you need to explain how a millimeter scale distortion in the solar surface can overcome magnetic forces strong enough to accelerate particles to nearly the speed of light. Nobody has managed that explanation because the physics doesn't support it. But consensus is not the same as certainty. And there are corners of the field where different questions are being asked. What if gravity isn't the relevant force? What if the sun and the planets are connected not through gravitational attraction, but through electric currents flowing in the plasma of the heliosphere? This is the territory of plasma cosmology and electric universe hypotheses, which sit outside the mainstream and are often regarded with skepticism by conventional astrophysicists. But the core idea is worth stating clearly. The sun emits a stream of charged particles, the solar wind, which carries electric currents and magnetic fields throughout the solar system. The planets, each with their own magnetospheres, interact with this wind. They create wakes, bow shocks, current sheets. They modulate the flow. Some researchers propose that when multiple planets align, their combined influence on the heliospheric current could feed back to the sun, not through gravity, but through electromagnetic coupling. The heliosphere is not empty space, with planets scattered through it. It's a structured plasma environment with current systems, magnetic field boundaries, and regions where charged particles flow in organized patterns. The Parker Solar Probe and Voyager missions have mapped some of these structures, revealing complexity that wasn't anticipated by earlier models. The solar wind doesn't blow uniformly. It's threaded with filaments, sheets, and regions of enhanced or depleted density. The planets move through this structure, and their magnetospheres interact with it in ways that create measurable disturbances. Could those disturbances propagate back to the Sun? Could they influence the timing of magnetic reconnection events that were already primed to happen? This is the question that plasma cosmology researchers are asking, and it's not an unreasonable question even if the mainstream hasn't embraced it. Is this proven? No. Is there direct observational evidence? Not in the sense that would satisfy most physicists. But there are anomalies in the data that haven't been adequately explained. There are periodicities in solar activity that seem to match planetary orbital periods. There are historical events where major flares coincided with specific alignments. One of those events happened in 1936. March 1936 saw a rare grand trine in the zodiac, a geometric pattern where 3 or more planets form roughly equilateral triangles as seen from the Sun. This happens occasionally, but what made 1936 unusual was that it occurred during a solar maximum, and the Sun responded with some of the most intense activity of that cycle. The data from that era is sparse compared to modern standards, but what we have suggests multiple X-class flares and severe geomagnetic storms clustered around the alignment period. The geomagnetic storms of March 1936 disrupted telegraph systems across North America and Europe. Auroras were visible as far south as the Mediterranean. Operators reported strange currents flowing through the wires, making communication difficult or impossible for hours at a time. The solar observations from that period show significant activity, though the classification systems we use today didn't exist yet, making direct comparisons challenging. Mainstream analysis attributes this to random chance. Solar maxima are chaotic. Flares cluster unpredictably. The fact that some of them happened to coincide with a planetary alignment is not evidence of causation. And this is a fair point. During any solar maximum, there are hundreds of flares spread over several years. If you look for correlations with planetary positions, you'll find them, because with enough data points and enough possible alignments, coincidences are inevitable. This is the multiple comparisons problem in statistics, and it's why scientists are rightfully skeptical of pattern matching exercises that don't have a proposed physical mechanism behind them. But the pattern keeps resurfacing. Every few decades, during an active solar cycle, there's an alignment event that produces stronger than expected solar activity. The scientific literature mostly ignores this because there's no accepted mechanism to explain it. But the pattern exists. It's not imaginary. 1958 saw another alignment during solar maximum 19, coinciding with some of the most intense geomagnetic activity of the 20th century. The alignment geometry wasn't identical to 1936, but it was close enough to raise eyebrows among the small community of researchers who track these things. Again, mainstream analysis filed it under coincidence. Again, the pattern persisted. So now we're approaching another grand trine, this time involving Mercury, Venus, and Jupiter in a near equilateral configuration as seen from the Sun. It's not exact. Astrologically minded observers might quibble with the orb, and astronomically minded skeptics would rightly point out that near equilateral can mean a lot of things, but the geometry is close enough to be noteworthy. And it's happening during solar maximum 25, at the exact moment when an unusually active sunspot group is rotating Earthward. Is the Sun responding to the alignment? Or is the alignment simply a convenient marker for a period when the Sun was going to be active anyway? This is where science, speculation, and ideology collide. because admitting that planetary positions might influence solar behavior feels uncomfortably like astrology, and scientists are trained to recoil from anything that smells like astrology. The distinction is important, though. Astrology claims that planetary positions influence human affairs through some mystical mechanism. What's being proposed here is electromagnetic modulation of a plasma system by bodies with measurable magnetospheres moving through a structured heliospheric environment. That's not mysticism. It's physics. Speculative physics, yes. Unproven physics, absolutely. But physics nonetheless. The challenge is that any discussion of planetary influences immediately gets grouped with crystal healing and horoscopes in the public imagination, which makes it professionally risky for scientists to engage with the topic seriously. There's a stigma. Researchers who explore these correlations often do so quietly, publishing in obscure journals or presenting at small conferences where they won't face immediate dismissal from their peers. This creates a strange situation where potentially interesting questions don't get the scrutiny they deserve because asking them feels too much like validating pseudoscience. And then there's 3I Atlas, the interstellar comet that entered our solar system in 2020 and is now somewhere in the outer reaches, slowly fading as it heads back into the void. Interstellar objects are rare. We've only confirmed a handful. They come from other star systems, carrying with them dust, ice, and potentially traces of the magnetic field structures from their stellar origins. 3I Atlas behaved strangely during its passage through the inner solar system. It brightened unexpectedly, suggesting outgassing activity that wasn't predicted by standard comet models. It showed spectroscopic signatures that differed from typical solar system comets, which makes sense given its extrasolar origin, but also raises questions about what else might be different about objects formed in other stellar environments. Could an interstellar comet influence solar activity? Directly, almost certainly not. It's too small, too far away, too insignificant in terms of mass or energy. But here's the speculative angle. If the heliosphere exists within a larger galactic current sheet, and if that current sheet carries structure and variability on scales we don't yet understand, then an object passing through from interstellar space might trace a path through regions of higher or lower current density. It wouldn't cause anything, but it might arrive at the same time as other perturbations in the galactic environment that we can't yet detect. The galaxy is not static. It rotates. The solar system orbits the galactic center once every 230 million years, moving through regions with different densities of dust, gas, cosmic rays, and magnetic field structures. We know that the sun's heliosphere changes shape depending on the local interstellar medium it's moving through. The Voyager probes detected the heliopause boundary where the solar wind meets the interstellar medium, and that boundary is not smooth or uniform. It has structure. Could that structure influence solar activity? Could variations in the galactic environment affect the sun's magnetic dynamo or the stability of its corona? These questions are so far outside current observational capabilities that they barely qualify as hypotheses. They're more like interesting things to wonder about while waiting for better data. This is piling speculation on top of speculation. It's worth acknowledging that clearly. But it's also worth noting that we've only been measuring the heliosphere in detail for a few decades. The sun has been operating for 4.6 billion years inside a galactic environment we're only beginning to map. There could be influences, cycles, periodicities that we haven't recognized yet because we haven't been watching long enough. The sun exists inside multiple nested systems. It's embedded in the heliosphere, which is embedded in the local interstellar medium, which is embedded in the Orion spur of the Milky Way, which is embedded in the larger galactic structure. Each layer has its own dynamics, its own timescales, its own ways of transferring energy and information. Assuming that the sun operates in isolation, influenced only by its internal processes, might be an oversimplification. Or it might be exactly correct. The burden of proof is on the people claiming external influences, and that proof hasn't materialized. The question is not, are planets causing flares? The gravity-based version of that question has been answered, and the answer is no. The more interesting question is, are planets synchronizing releases? Are they acting as pacemakers in a system that's already primed to erupt, not adding energy, but modulating the timing of when that energy gets released? Think of it like a dam that's already cracked and ready to fail. You don't need to add more water to make it break. You just need the right vibration at the right frequency to push it over the edge. Could planetary alignments be that vibration? Could they provide just enough electromagnetic perturbation to tip an already unstable magnetic structure into reconnection? If the answer is yes, it doesn't mean astrology was right. It means plasma physics is more complicated than we thought. It means the heliosphere is more interconnected than the models currently assume. It means we're missing something. And if the answer is no, if January 18th through 20th comes and goes without major solar activity, then we learn something too. We learn that the correlation patterns are coincidental, that the convergence window is a psychological artifact, that the sun truly operates independently of its planetary environment. Either way, the window matters, because in 5 days, we'll have data instead of speculation. If the sun is responding, the next question is, to what?